Welcome. This session we will try to solve a continuous beam using flexibility matrix method. See here I have considered a continuous beam ABC having two supported spans. Span AB 12 meters, span BC also 12 meters, where span AB has got 40 kilonewton per meter UDL and span BC has got eccentric point load. It is 4 meters from B. Okay, so how do you solve this problem using flexibility matrix method? So let us try solve this step by step procedure. So first let us identify what is static indeterminacy of this problem. Okay, right. So to find static indeterminacy of this given problem, total number of reactions minus total number of equilibrium equations. So total number of reactions to calculate. You see the support reactions here are 2, neglecting the horizontal reaction, 1 here and 1 here. So there are total 4 reactions, and same way neglecting horizontal equilibrium equation, you have 2 equilibrium equations. So it is 2. Static indeterminacy of this given continuous beam is 2. Right. Now let us write the unknown reactions present in this problem. So I'll start from support A. So moment at A, reaction at A. These are the unknowns. Reaction at B, reaction at C. So these are the unknown reactions. By removing the external supports that you get them. And there is another unknown which you don't see it when the beam is continuous. So this support B, due to its continuity, you have moment at B. This is internal. These are all external reactions. Okay, this set that you see is external reactions and this is internal reaction. Okay, so as the static indeterminacy of this problem is 2, so you need to choose redundants. What are redundants? The number of excess support reactions present in the structure to keep the structure in equilibrium. There may be required maybe some number of reactions they are required to keep this structure in equilibrium. So if you find any support reactions in excess of those reactions, so we call them as redundants. You see here I have got so many reactions given here, but this number says there are 2 reactions in excess of those required. So you choose any 2 among these so that the structure becomes determinate. Okay, so now I'll choose MA, MB as redundants. Okay, so you may choose any of these, any 2 from these. Okay, right. So now I have chosen MA, MB as redundants. Okay, now I shall assign coordinates. okay, to these the chosen redundants. So I call MA as 1, MB as 2. Okay, right? So in diagram, how do you represent them? So as MA is redundant, you remove that redundant. So if you remove the reaction MA, you get a hinge there, okay, instead of fixed support. Now the coordinate is 1 here. Same, removing MB means removing continuity, means break the beam here. Okay, so now the beam becomes, the given continuous beam becomes two simply supported beams. Okay, now I give the coordinate like this, coordinate 2. In the positive sense, this creates a sagging here, this creates sagging here. So these are the coordinates, which is MA given as 1, MB given as 2. Okay, so now your job is to find these two, the extra unknowns, those are redundants. Okay, so these in matrix form, in flexibility matrix, we call this as P matrix. That means redundant matrix, MA, MB. So the entire procedure is to solve these two unknowns. Okay, right. So you know, to solve this problem, you need excess number of equations, because equilibrium equations are not sufficient. You see, there are only two equilibrium equations, but the unknowns are four, so two more equations are required. So those equations are called compatibility equations. Okay, so I need compatibility equations to solve those two excess unknowns. So now I'll write that compatibility equation. So you might have learned this. P is equal to F inverse delta minus delta L. So these are the compatibility equations. The number of equations depending on your static indeterminacy. So in our case, the SI is 2, which means there are two equations in this. Okay, so if I try to expand this, MA, MB are my redundants. So you have SI value 3, I will have 3, okay, 3 by 1 matrix here. Now I'll have F11, 1, 2, 2, 1, 2, 2. Inverse. Now delta 1, delta 2, delta matrix minus delta due to loads, delta 1 L, delta 2 L due to loads. Suffix L denotes loads. So these are the two equations that are required for solving this given problem. Okay, so now your job is to formulate this flexibility matrix, finding its inverse, formulate this displacement matrix, and this displacement matrix due to loads. This is our job. Okay, now first let us write this delta matrix, which means delta 1, delta 2. Okay, what is 1 means? A. Delta means displacement. So as your redundants are moments, displacement will become, corresponding displacement is rotation. That means theta A. 2 means B. We have given coordinates, right? So So in the given problem, theta A is 0, theta B is also 0. Okay, so this matrix is ready now. Now going to develop displacements due to loads alone, delta 1L, delta 2L. Okay, which means one means A, so theta A due to loads, theta B due to loads. Okay, right. So we'll try formulate this matrix. So now you consider the released structure. Released structure means what? Remove the redundants. So the structure that you get after removing the redundants is released structure. So I'll draw that released structure. So here you have removed MA, so you got a simple support there, and you broke the beam here, so you got another simple support here. So now you take only the loads. So your job is to formulate delta L. So take only the loads. So there is UDL present on this beam. This is AB. UDL value given is 40 kilonewton per meter in the given problem. Just an example problem. 12 meter span. Okay, now what I want is theta A and theta B, right? So this beam due to the loads will bend like this, simply supported beam. So this rotation of this point A is clockwise, and the value of theta A, so from your earlier study you know that simply supported beam with UDL, the slope at one end is WL cube by 24 EI. Same at the other end also, theta B, because of symmetry this also is same. Okay, so I name it as L, suffix L. Okay, so now the value is substituting these values like 40, 12 cube by 24 EI will give you a value 2880 by EI. Okay, right. Now let us go to the other member. There are two such members. Now member BC we are talking about. You have an eccentric point load of value 120, which is at 4 meters from B or 8 meters from C. Put together it is 12 meters. Okay, now this beam also bends. I'll try to draw the bending nature. Because of eccentric load, the slopes are not same at both the ends. See, there will be more slope here because load is nearer to B. Less slope here, now farther from C. Okay, so what will be the value of theta B again? So you have theta B also from AB. Now you have theta B from BC. Okay, so I'll call this as 1, call this as 2, or you can say member AB here, member BC here, just to identify. So theta B value here, you have got a formula that you have earlier might have been learnt earlier. Otherwise you can work out on your own such values by conjugate beam method. Okay, PAB by 6 EIL L plus B. So this I call it as A, this I call it as B, and this is L. Okay, now you see p value 120, 4, 8 by 6 EI, L is 12, 12 plus 8. Okay, so this works out to be 1066.67 by EI. We don't want theta c value. Okay, so I'm not going to calculate that. So you see theta a value is 2880 by EI, whereas theta b you have two values, one from AB and the other one from BC. Okay, both are in their coordinate directions. If you remember, we have given coordinates like this for the beams which we broke the beam. Okay, so this bending is also in the same direction, it's also in the same direction, so both are following the moment direction, so they are positive slopes, so both are to be added. So 2880 by EI plus 1066.67 by EI. So put together the value is 3946.67 by EI. Okay, so now our delta matrix is ready. I'll write it, which is equal to 2880 by EI 3946.67 by EI. So this is our delta L matrix. Okay, right. Next, so once you have formulated the delta matrix and delta L matrix, now it is our job to develop flexibility matrix and inverse of it, okay, to substitute into the compatibility equations. So let us try solve or evaluate this matrix. Okay, as you have static indeterminacy value is 2, so your the flexibility matrix will become 2 by 2. You have SI value 3, it will be 3 by 3. Okay, so here we will be finding these values. Okay, so because of symmetry, F12 is equal to F21. Okay, so how you find these values? So give 1 kilonewton meter means 1 unit force. Okay, here your redundant is moment, that's why I'm giving 1 unit moment. If your redundant is force, I'll give 1 unit force. Okay, so 1 kilonewton meter moment at each coordinate. Okay, and find corresponding slope, because corresponding displacement to the moment is slope at all the coordinates. Okay, so now I give 1 kilonewton meter, say this is member AB. You have to work with only the release structure. Now this is member BC. Okay, now first coordinate is at A, So this is the direction of coordinate and I shall give 1 kilonewton meter moment. Because of this, what is slope at A? That means coordinate 1. That is F11. Okay. So if this is rotated, this is going to bend like this. Like this. Okay. So the slope here is your F11 value. That means theta A value. So this value is ML by 3EI. Okay. When a simply supported beam is applied by moment at one end, slope at the same end is ML by 3EI. Slope at the other end is ML by 6EI, half the value. Okay. So what will be this value now? F21. Okay. Because coordinate 1 is J here, Fij, that what you have learned. Okay. J is your force coordinate, Fij. Okay. J is force coordinate where you have applied the force. I is the displacement coordinate. Okay. So that is how we work out flexibility coefficients. Okay. Right. So working out for this value, M is 1, moment applied is 1, L is 12 by 3 EI, which means 3 fours 4 by EI. So half of this value is 2 by EI. Okay. So this is how you got this F11 and F21, which is same as F12. Okay. Now coming to the F22 value. So member AB again, then member BC. Okay, now give 1 kilonewton meter at coordinate 2. So this is our coordinate 2, means moment at B. So B means there are two members meeting at B. So you will have beam AB, the end B, beam BC also end B. 12 meters, 12 meters. Okay, so now I need F22 value, means coordinate 2 means B. I applied 1 kilonewton meter. Coordinate 2 means again B. I need slope here. So this is going to bend like this. So this theta value. This is going to bend like this. This theta value. So you see both are following their moment direction. So both are positives. So and they are at the same end of moment applied. So they both are ml by 3 EI plus ml by 3 EI. Okay, don't write adding these 2 ml by 3 EI because sometimes the length may be different in your other problems. Okay, don't straight away add these two. Okay, first substitute, then you add. Okay, so now both put together it is 8 by EI. Okay, so now F matrix is ready. I'll write the F matrix. The flexibility matrix is now taking 1 by EI common. So first value F11 is 4 by EI. This 2 by EI, 2 by EI and 8 by EI. This is our F matrix. Now finding F inverse, you need inverse matrix, right? So inversing this will give you EI, okay, divided by determinant 32 minus 4, okay, so it is 28, 8 minus 2 minus 2, 4, okay. So this is inverse of the matrix, okay. Right, now substituting in the compatibility equation, this PH is equal to MA MB F inverse. This is EI by 28, 8 minus 2 minus 2, 4 into delta matrix. You remember is 0, what we have evaluated. And also this is the 2880 by EI and 3946.67 by EI. Okay, now simplifying this, so will give us the moment values. So EI by 28, 8 minus 2 minus 2, 4. So this will be 0 minus 2880 divided by EI, 0 minus 3946.67 by EI. So EI is common, you can just get it out. So EI gets cancelled, okay. So it is simply 1 by 28, 8 minus 2 minus 2, 4 minus 2880 and minus 3946.67. So if you solve for both the values, like row column operation, first row and this column, and then second row and this column multiplication, so you'll have MA value is equal to 1 by 28, or you can use your calculator straight away, it will give you the multiplication value. If you want manually, you can do like this: 8 into minus 2880 plus minus 2 times minus 3946.67. So this works out to be minus 540.95 kilonewton meter. Similarly, MB value 1 by 28 minus 2 times minus 2880 plus 4 times minus 3946.67, which works out to be minus 358.1 kilonewton meter. So these are the redundants that are present and you have chosen them, okay, as part of your solution. Now let us plot BMD. Okay, so for the given beam, I'll try plot it below. So this is the given problem. Having two equal spans but of different loads. Okay, so this is of UDL 40 kilonewton per meter. This is of eccentric point load 120 kilonewton. This is of 8 meters and 4 meters. So let us try plot the BMD. So dropping this point down, dropping this down, dropping this down for drawing end moment diagram first. For indeterminate structures, we draw the BMD as end moment diagram and overlapping the span moment diagram. Okay, so now you got end moments as moment at A is 540. Let us locate that 540.95 and 358 somewhere around this 58.1 and moment at C is 0 because it is simple end. So just join these by straight line. Will give you the end moment diagram. Now overlapping with the span moments. So treating this as simply supported beam with UDL, the bending moment value is maximum at center, that is WL square by 8. So the midpoint location roughly works out to be 720 kilonewton meter. So you need to plot a parabola, which would look like this. Same way, maximum bending moment occurs under point load. So it's like PAB by L, so which would work out somewhere around 320 kilonewton meter. So just joining by straight line. Right. So let us hatch the net BMD. So this is going to be the net bending moment diagram. So this is hugging negative, this is sagging positive, and this is hugging negative, this is sagging positive. So this is the complete solution for this question. Right, thank you.